Welcome everyone to the second talk in the CAP lecture tour series for 2022. Dan, did I jump the gun?
I think I should start.
Okay, my apologies.
Okay. Good afternoon. My name is Dan Xiao from University of Windsor, and I am a regional coordinator for the 2022 CAP lecture tour. Before we get started, I have a couple of announcements about how the talk will proceed. All questions will be handled at the conclusion of the speaker's presentation. Please post your questions in the Zoom chat at any time. The questions will be posed anonymously to the speaker by the MC. All students participating today are encouraged to remain after the talk and participate in a 30 minutes breakout informal discussion session with the speaker. We also invite any faculty or other attendees from the host institution to participate as well. Unfortunately, we're not able to activate the French captioning for the speaker's live presentation. However, after this event has concluded, YouTube's captioning feature could be used to watch this lecture on the CAP YouTube channel with French subtitles. Now it gives me great pleasure to introduce our host for today's CAP lecture tour talk, Professor Patrick Hall from the Physics and Astronomy Department at York University, who will introduce our speaker.
Thank you, Dan, and apologies for jumping the gun earlier. Welcome everyone to the second talk in the CAP lecture tour series for 2022. I am Patrick Hall, and I'm pleased to host this talk on behalf of the Physics and Astronomy Department at York University. We had hoped to be able to have this talk in person at York and to stream it across Canada, but with rising COVID-19 cases in January, the decision was made to have this lecture tour purely online. The lecture tour is sponsored by the CAP Foundation and the Canadian Association of Physicists, or CAP, which is a national network of about 1,700 physicists working at universities, companies, and research institutions across Canada. The CAP works on behalf of Canadian physicists to support physics education and research, and sponsors a number of physics activities, including this lecture tour and national research conferences. The CAP also delivers a number of programs for undergraduate and graduate students, such as research conferences, physics scholarships and prizes, and a student advisory council. If you have not already joined the CAP, please consider becoming a part of Canada's largest network of physicists and physics students. It's free for undergraduate students, and the first year of membership for graduate students is free as well. Today's talk will be 45 minutes, followed by 10 minutes for questions. If you would like to pose a question to the speaker, you can type your questions in the chat at any time, and one of the moderators will ask the question at the end of the talk. Following the talk today, you will have the option to join a breakout room where you can speak directly with the speaker, ask additional questions about the research presented, or about related career paths. Now it gives me great pleasure to introduce today's speaker, Dr. Seyda Ipek from the Department of Physics at Carleton University. Dr. Ipek's research focuses on the study of beyond the standard model physics. Today, Dr. Ipek will present her talk entitled, "Why Are We Here? Matter-Antimatter Asymmetry of the Universe." Welcome, Dr. Ipek.
Thank you very much. I will... Thank you very much for the introduction. Yes, so today I will tell you about a mystery in our universe, which is the matter-antimatter asymmetry. Before going to the specific mystery, I want to go through a very brief history of our universe, mentioning just a few other stuff that we don't quite understand about our universe.
Dr. Ipek, I believe
Yes.
your slides are not yet appearing as shared.
Interesting. It seems like It's sharing. It's sharing now.
I don't see them, but perhaps someone from CAP can confirm that they don't see them either.
No, they're not available yet.
Okay. I will try it again. All right, do you see it now?
No, I can stop my sharing to see if perhaps it works when I'm not sharing.
I can see them from here.
Oh,
There
Yes,
they-
now it's good.
okay, perfect.
Welcome, Dr. Ipek.
All right, yes. So starting over, yes. So I'm going to tell you about a mystery in our universe, which is the matter-antimatter asymmetry. But before going into this specific mystery, I want to go through a very brief history of our universe and mention some other things that we don't understand about it. So the overarching theory about the origin of our universe is that it started with a Big Bang, followed by a period of an era called inflation, where the universe was expanding very fast from a very, very small space-time. At this point, the universe was very hot. As particle physicists, we equate temperature with energy by setting the Boltzmann constant to 1. So if you know your thermodynamics, you would remember that energy goes like kBT. And if you just set kB to 1, you can think of temperature as energy. And this is all to say that the universe was very energetic because it was very hot. We actually don't understand inflation that much. There are many theories out there. We also don't know why it ended or when it ended exactly. And after inflation ended, all of the stuff in the universe was produced somehow by a mechanism that we don't know the details of. But let's say that this happened and the stuff inside the universe was formed somehow. As the universe ages, or as the time goes by, universe continues to expand, and as it expands, the temperature of the universe actually goes down. So it becomes cooler and cooler. When the universe's temperature goes down to about 100 giga-electron volts, this is still very hot temperatures, but energy-wise, it's low for us. And this is when the universe was about a nanosecond old. An interesting transition happened where all of the particles become massive. Not all the particles that have masses acquired their masses through the Higgs mechanism. So this is one era in the universe that we think that happened, but we don't have any proof that this era actually happened. After this, the universe continues to expand and cool down. And when the universe is about a few seconds to a minute old, and the temperature was about 1 mega-electron volts, this is when light nuclei like helium, deuterium, even lithium start forming. So these are the first atoms in the universe that started forming, basically. At this point, we know that there was only matter in the universe and there was no antimatter. And this will be the majority of my talk, of course. And so I will come back to this era again. As the universe continues to expand and cool down, it cools down to a temperature of about 3000 Kelvin when it is 380,000 years old. So it's quite old now, but compared to what it is now, still young. This is when electrons in the universe, they start binding to the nuclei, forming neutral atoms. So for example, the helium nuclei will just capture 2 electrons so that the helium atom itself will be neutral. When this happens, the photons inside this primordial soup can escape, and then we observe these photons as the cosmic microwave background. And it gives you this beautiful picture, and this is basically a picture of a snapshot of our universe when it was 380,000 years old. After this, so at this era, we can look at the cosmic microwave background and tell what is in our universe. And due to this observation of cosmic microwave background, we know that our universe has ingredients that are called dark energy and dark matter that we don't understand what they are. After this era, there's a lot more interesting stuff happening in the universe. There's an era when the first galaxies or first stars were being formed. There's a period that we cannot observe that well. These are called dark ages. Here I put a picture of one of the undergraduate students that work with me, Melissa Sammet, who is studying a phenomena that is observed in dark ages. And after the period of dark ages, there's very fertile grounds for galaxy formations and stuff. And this is when our universe is very cold. When our universe is about 5 billion years old, our solar system forms. And now here we are, and our universe is 13.8 billion years old. So this is a very brief history of our universe. And as I told you just a few slides ago already what is in our universe, but it is actually very important for both particle physicists, cosmologists, and astrophysicists to know exactly what is inside, what is inside the universe, or what kind of materials contribute to the energy density of our universe. This is a picture taken by the Hubble Space Telescope of very, very young galaxies. This is when our universe is only a few hundred million years old. So these are very, very young galaxies at the time. The stuff you see here by eye, so all of the light that is coming from, and even some of the stuff that you don't see by eye, but telescopes like X-ray telescopes pick up. So whatever we can pick up with our telescopes, that is called ordinary matter or luminous matter, or sometimes called baryonic matter. That kind of matter that makes up the stars and us and stuff that we can easily observe with our telescopes, that is only 5% of the things that is inside our universe. So 5%. Another 25% of our universe is made up of an energy called dark matter, or a material called dark matter. We don't know what dark matter is. We can detect it through its gravitational interactions, but other than that, we don't know what it is. That's why it's called dark. We know that it doesn't radiate much, if not anything. And then there's another energy, type of energy called dark energy, and that's 70%. That's by far the majority of our universe is made up of dark energy. It probably is the reason why our universe's expansion is accelerating, but we also don't know what it is at all. So we don't understand basically 95% of the energy density in our universe. But today, I'm actually going to tell you another mystery about the ordinary matter in the universe. So we think that we understand ordinary matter, but there's still quite a few things that we don't understand about ordinary matter. And let me make more concrete what I mean by ordinary matter. So when we look around, even just to our frozen river that you see in this picture, or to our sun, again, you see a frozen sun in this picture, we can look at our galaxy and beyond. All of these things are primarily just made up of atoms. They can be a carbon atom, hydrogen, helium, some iron, what have you. So all of these atoms. And then when we look closer to atoms are just a collection of protons, neutrons, and electrons. These are smaller units than an atom. And then we can take a proton or neutron, and we can look inside the proton and neutron, and they are made up of even smaller things that are called elementary particles, like quarks and gluons. Electron that goes around a nucleus or around the proton, that's also an elementary particles. Elementary particles are stuff that we cannot divide anymore. They are the elementary units of beings in our universe. These elementary particles make up the ordinary matter, and we also understand them. They are described by what is called the standard model of particle physics. So there are only a finite number of elementary particles, and we can put them into a table like the periodic table with respect to their specific properties and similarities. There are 4 groups of elementary particles. One group is called quarks. So these are particles that make up the proton and neutron. For example, a proton is made up of 2 up quarks and a down quark. These have names like up, down, charm, strange, top, and bottom. There are 6 of them. And their defining property is that they interact via what is called the strong nuclear force. And then there are other types of elementary particles called leptons. The well-known or familiar of leptons is the electron. We know that electrons are just they go around the nucleus in an atom. Electrons, there are leptons that are very similar to electron called muon and tau leptons. These are exactly like the electron, except that they are heavier. For example, muon is about 200 heavier than the electron, and then tau is about 2,000 times heavier than the electron. And then there are types of leptons called neutrinos. We observe neutrinos coming from sun, coming from supernova. We produce a lot of them in nuclear reactors, for example. These are chargeless particles, and they interact very little with other stuff. They also have very interesting properties that I research on, but I will not go into today. There is, of course, the Higgs boson, maybe the most popular of the elementary particles. Higgs boson was also the most recent discovery within the standard model. So it was discovered in 2012, even though it was hypothesized in 1960s. Its discovery took a long time, and it is the particle that is responsible for giving mass to many of the other standard model particles. It is one of its kind. It's called the scalar particle, and it also plays a very big role in the early universe as well, which I will not go into more details in today. The third group, or the fourth group, let's say, of elementary particles are called force carriers. These are gauge bosons in mathematical terms. These of course, these are associated with mediating the forces of nature. So you might remember from your physics classes that there are four forces in nature. One of them is gravity. The other one is weak nuclear force. This is responsible for example, beta decay and how nuclear reactors run. There is the electromagnetic force. This is just the regular electromagnetic force that we know. And there is a strong nuclear force. This is what binds basically proton and neutron to each other. Each of these forces are carried by elementary particles called force carriers. For example, the force carrier for electromagnetic force is a photon. For strong nuclear force, it's called the gluon, and for weak nuclear force, the force carriers are called W and Z bosons. W and Z are just some literally the letters. The W boson is charged, so there is a W plus and a W minus. The gravity is probably carried by a particle called graviton, but gravity doesn't really fit into our understanding of the standard model, so this is left out of that, left out of the standard model table, basically. These forces and the elementary particles of the standard model and their interactions through these forces are described by certain equations. And there are, well, everything in physics, we like to describe them by equations. And you might have seen many or all of these equations before. For example, we use classical mechanics to describe large and slow objects. We use general or special relativity to describe the motion of very fast things or extremely heavy things. We use quantum mechanics, non-relativistic quantum mechanics, to describe smaller objects that are not moving too fast. And then we have a tool called quantum field theory to describe the interactions of elementary particles. And since elementary particles are very often very light, they are often very relativistic, meaning fast, and their behavior or their mechanics is described by what is called quantum field theory. Now, you can see that many of these equations are just differential equations. A physicist's job is often just solving differential equations, and as often the case that your differential equations become more and more complicated as you try to understand something better and better. So the differential equations will come up again when we try to understand how we can generate an asymmetry between particles and antiparticles. And when I say antiparticles, I want to let me describe what I mean as well. So the standard model actually doesn't only consist of the table that I showed you. Those are the elementary particles in the standard model, these equations that describe the standard model or describe the interactions of elementary particles, they also predict what are called antiparticles. For example, for an electron has electromagnetic charge -1, and it has a mass of 511 keV over c squared. The same equation that describes the motion of an electron also predicts that there will be an anti-electron. An anti-electron will have the exact same mass as the electron. It will just have negative, it will have opposite charges, meaning if an electron has -1 electromagnetic charge, the anti-electron is going to have +1 electromagnetic charge. The anti-electron is actually called positron. It was discovered actually before the idea of antiparticles were formalized by Dirac. It was just thought to be a strange electron, or a weird electron, basically. Just like electrons, other elementary particles, like for example, quarks, have antiparticles. For example, they are called antiquarks. And just like quarks can come together to make a proton, antiquarks can also come together and combine into making an antiproton. You can even make an anti-hydrogen just by fusing antiproton and positron, anti-electron together, right? Because the proton and electron makes a hydrogen, and antiproton and anti-electron makes an anti-hydrogen. We know that from our both from our equations and from our experiments, we know that antiparticles have the same mass as their particle partners. They just have opposite quantum charges. And whenever I say a quantum charge, you can think of the electromagnetic charge that we have, but there are also other charges associated with the other two forces, the weak and strong nuclear forces as well. And antimatter is nothing bizarre, really. It's very normal. We meaning theorists, and both theorists and experimentalists understand what antimatter is. We can make a lot of antimatter. The previous place I worked at, a national lab in near Chicago in the USA, it was called Fermilab, and they had a particle collider called Tevatron. And this at the Tevatron, they collided protons and antiprotons. So they would make about 10 to the 10 antiprotons per hour, and then they would just collide them with protons and just look after, what happens after those collisions. Tevatron became, it shut down after a much larger particle collider was turned on. This is the Large Hadron Collider at CERN. So there's a collider going between the France and Switzerland border. It is very large. It is 28 kilometers in circumference. And at the Large Hadron Collider at CERN, they collide protons and protons. So it's not an antiproton-proton collider, but it's a proton-proton collider. But after these collisions, you produce antimatter as well as matter as well. So you can also study the properties of antimatter too. We have a group here that works for one of the experiments that is done at the Large Hadron Collider called ATLAS. So from all of our studies and theories, we know that antimatter already exists as predicted. We also know how they behave quite well, actually, not perfectly, but to a degree that tells us that when matter and antimatter just come close to each other, they annihilate, meaning they just destroy each other. For example, if you bring an electron and a positron in the vicinity of each other, they will just combine, and then they will just turn into pure energy, maybe through photons. So this is observed, this is expected and observed. It also tells us that if there was any antimatter around us right now, like if there was an anti-Seyda in this room, or if there was some anti-cat, we will just attract each other, and then we will just go poof. We will just turn into pure energy. We won't be in our current form right now. Right? So it is good that there's no antimatter, because if there was, we wouldn't be here. But here we are, that's because there's no antimatter, as I keep saying. But the reason that there's no antimatter is not well understood. Why is there no antimatter? And what do we mean by why there is no, or what do we mean when we say there's no antimatter or matter-antimatter asymmetry. We can actually measure this asymmetry, meaning the abundance of matter over antimatter, because it affects how our universe behaves, especially in its earlier form. For example, if we can look at the cosmic microwave background, this is when electrons bind to nuclei to form neutral atoms. And when they form neutral atoms, universe becomes neutral for photons to escape. So the photons in our universe, they can escape. And this happens when the universe's temperature is about 3000 Kelvin. So that means that those photons also have energies at about 3000 Kelvin, but the photons, they travel throughout time, which was a while ago, and then they get what is called redshifted. And when we observe them now, their energy or their temperature is about 2.7 Kelvin. And this picture shows us the energy of those photons. So here the red dots are a bit warmer photons, and blue ones are a bit colder photons. So they're all around 2.7, but some of them are just a bit colder, some of them are just a bit warmer. And the correlation between two photons on this map depends on a lot of parameters, but one of those parameters is what is called the baryon to photon ratio. And this is a way to see how many more matter particles we have over antimatter particles. Baryon means, so baryons are made up of quarks, for example, like protons and neutrons. So they are larger particles. They are not elementary particles. And whenever I say baryon, you can just swap it for a proton or a neutron if you want. So this quantity eta is called the baryon to photon ratio. It measures the difference between the number densities of baryons and antibaryons. So this NB is a number density of baryon, and NB bar is a number density of antibaryon. So this NB minus NB bar over the number density of photons. This is a dimensionless quantity, which is nice to keep track of as the universe ages, because since it's dimensionless, it actually doesn't change as the universe ages. So it's a good parameter. And measured from this cosmic microwave background by the Planck satellite in 2015, eta is we know that this asymmetry is about 6 times 10 to the minus 10. We can also measure it at an earlier time in the history of our universe. This is when the first nuclei were forming. So these are not full. They don't have their electrons yet. But when the first protons and neutrons, they were just binding together or fusing together to form nuclei. This happened when the universe was about a minute old. So cosmic microwave was when it was 400,000 years old. Big Bang nucleosynthesis happens much earlier, when the universe is a minute old. At this point, protons and neutrons, they come together to form stuff like deuterium, and then deuterium can come together to form atoms like helium-3. Helium-3 and deuterium can come together to make helium-4, and then you can go up to making lithium and beryllium as well. So these are the first elements in our universe. And a little fun fact is that all of the deuterium we observe in the universe now actually was made at this point. Deuterium is a very special nuclei, and I won't go into details. So this plot here is showing you the abundances of these elements that is expected from the standard model and standard cosmological models versus the baryon to photon ratio. So the x-axis is eta parameter from the previous slide, and the y-axis is the abundances of these light nuclei that were formed in Big Bang nucleosynthesis. And the bars, the yellow bars are observations of these elements. So the first one is for helium-4. And there's a tiny one on the deuterium line, a tiny yellow bar, because deuterium is observed very well. And the vertical bar is the observation of eta, or the measurement of eta from the cosmic microwave background, that is labeled as CMB. You see that the deuterium observation agrees very well with the CMB observation of eta. So that's a good sign. They agree very well. The helium is not observed very well because helium is made in in stars as well. So it's hard to tell which helium is coming from this primordial Big Bang nucleosynthesis era versus which ones are coming from the sun, basically. But they also agree with the standard, with the cosmic microwave background measurement. One of the other undergraduate students I work with, Tammy Chowdhury, she is looking at this era, the BBN era, to answer another mystery about the standard model. So overall, then we know this asymmetry exists, and we know we can quantify the asymmetry. The eta parameter is about 10 to the minus 10, and that means that there were basically one extra quark for every 30 billion or so quark-antiquark pairs in the early universe. So there was one extra quark for every basically 20 billion pair of quarks and antiquarks. And like, how do we make sure that we can produce such an asymmetry? Why would the universe have that one extra quark? Well, to do that, the physics, as we understand, needs to be just a little bit different between matter and antimatter. We think of them as very similar or almost the same, except they're opposite quantum charges. But actually, there needs to be a difference because we want to have one extra for every symmetric pair. In order to make sure that our physics for the universe produces that extra pair, our physical models, like the standard model, needs to follow 3 rules. These are called Sacral Conditions, and I will explain in detail what these conditions mean, but let me just go through them very quickly now. So the first condition is that a quantum number called Baryon number cannot be a conserved quantity. Charge and charge parity symmetries also must be violated. They can't be good symmetries in a universe with asymmetry. And there needs to be some out of equilibrium process. These are called Sakura Conditions after a great Russian physicist named Andrei Sakharov. Andrei Sakharov was not only a great physicist, he was also an extreme, a well-regarded humanist. He worked for anti-nuclear weapons and generally just anti-war and anti-weapons. There's a human rights prize named after Sakharov. So let's understand what these conditions mean, or what do we mean by our universe needs to satisfy these conditions. And let's start with what we mean by baryon number. The baryon number is just a quantum charge, like the electric charge. It's a quantum number. Each quark has a baryon number 1/3. This is the charge that we assign to make sense of some mathematical properties between quarks and other particles. So quarks have baryon number 1/3, and proton is made up of 3 quarks. So proton has baryon number 1. Since it's a quantum charge, the antiquark will have the opposite baryon numbers. Antiquarks have -1/3 baryon number, and when 3 antiquarks become an antiproton, the antiproton has a baryon number of -1. This quantity delta B measures the net baryon number. It is the number of baryons minus number of antibaryons, or really number of protons minus number of antiprotons, or number of neutrons minus the number of antineutrons. Neutrons also have baryon number 1. That's why they're called baryons. Very good. So our understanding of the universe, or I shouldn't say understanding maybe, but our idea of the beginning of the universe started with a period of inflation, and we have good reason to believe the inflation makes sure that this number delta B, or this quantity delta B, was 0 at the very beginning. So at the very beginning, we expect there were equal numbers of quarks and antiquarks, which just makes sure that there is a 0 net baryon number. This is at the very beginning. If delta B as a quantity was a conserved quantity, it will just stay as 0, right? That's what conserved quantities mean. They don't change in time. But we now know from our observations that delta B is not 0. In fact, delta B is associated with that parameter eta, which is about 10 to the minus 10. It is small, but it's non-zero. And in order for it to become a non-zero number, delta B cannot be a conserved quantity. It cannot be associated with a conserved current or conserved charge. So this is the requirement for baryon number relation. It really intuitively makes a lot of sense. This delta B, if you can calculate it with your model of the universe or your physics theory, it cannot be a conserved quantity. Another thing we need to make sure is that the physics laws that describe the interactions between our particles and antiparticles, they need to be able to tell the difference between a particle and antiparticle. And it's a very subtle point, and it can be very complicated to understand when you're writing down theories or working with hypothetical particles and interactions. But it boils down to understanding the symmetries between particles and particles and particles and antiparticles. And two of the symmetries that we work with a lot is related to handedness of particles and their parity. So handedness, you can think of an elementary, even though you should never think of an elementary particle as a spinning particle, without it technically does not have an intrinsic, it does not have a finite size. So spinning electrons spinning don't make really sense. But for all intents and purposes, you can think that. Let's think of electron as a spinning particle, so that there will be an angular momentum direction associated with it. And if a particle is like left-handed, its spin direction is anti-parallel to its momentum direction. So here, the first particle here is spinning in the minus x, and the momentum is going in the x direction. So I will call it a left-handed proton. We can do a charge transformation on this proton, meaning that we can turn the proton and change its quantum charges, which will just turn the proton into an antiproton. But it doesn't do anything to its spin or momentum. So it's still a left-handed particle, but now it's a left-handed antiparticle. And then a parity transformation just is a mirror transformation, meaning it takes a left-going particle or a left-going momentum, turns it into a right-going momentum. So if you do a parity transformation on this left-handed antiproton, you turn it into now a right-handed antiproton. You don't change its spin direction, but you change this momentum direction. So when successively done, this means a left-handed proton is now turned into a right-handed antiproton. If you have a way to differentiate between these two systems, so this means that if you have some physical laws, for example, a setup that can differentiate between a left-handed proton and a right-handed antiproton, that necessarily means that these two systems act differently, so that you can tell the difference. And that means that charge and parity symmetries are violated, meaning your system is not symmetric under these transformations, basically. And they shouldn't be, because our universe somehow differentiated between a left-handed proton and a right-handed antiproton, because we have a lot of left-handed protons, but we don't have any right-handed antiprotons lying around. So this means that if you think about our universe as our experimental setup, there was some way that the universe differentiated between these two systems. So this is the requirement for the charge parity violations, the second Sacral condition. We need to make sure that our physical laws that can tell the difference between these two systems. And the third condition describes or necessitates that the universe is out of equilibrium when the Baryon asymmetry or the Matter-Antimatter symmetry was being produced. This is also intuitively understood. If a system is in equilibrium, there's really nothing interesting happening, right? If two systems, for example, two systems are in equilibrium, if two heat paths are in equilibrium, there is no heat exchange between them. This happens when we think about how an asymmetry is produced as well. If something is in equilibrium, if you say you have a zero Baryon asymmetry and there's a process that produces a Baryon asymmetry, but if that process is in equilibrium, it will go in the reverse direction with the same rate, like a chemical reaction basically, and then it will just erase that asymmetry. So really nothing interesting can be happening in thermal equilibrium, and this is why it's important to have some out of equilibrium process. And I will come back to this point again. Now, when we know what conditions we need to satisfy to describe this or to produce an asymmetry, we can ask if our beautiful standard model, which already describes the particle physics in the universe, basically, if we can explain the asymmetry between matter and antimatter in our universe. So does the standard model, and the question can be rephrased as, does the standard model satisfy the Sacral conditions? And people have asked this. This is what Sakura started with as well. So we can look our standard model equations, which I really haven't showed you because they are horrendously long. But we actually know that baryon number is not conserved in standard model, specifically in weak nuclear interactions. This is from an observational fact that only left-handed particles interact with a weak nuclear force. There's no right-handed particles do not interact with the weak nuclear force, and this necessarily means that baryon number is violated. And it can be thought of as, if you have taken a quantum mechanics class, it can be thought of as through a potential like this. This is a sinusoidal potential. And let's think the stuff in our universe, like our universe as a soup of elementary particles, and it just sits in a potential like this. And this potential, the x-axis here is net baryon number. So right now our universe is very cold and it's sitting in one of the minima of this potential with some net baryon number. In order to change baryon number, it needs to tunnel through some quantum tunneling process. And quantum tunneling can happen, but it's extremely hard. For our universe to tunnel to a vacuum with a non-zero baryon number, it would take about e to the 160 years, basically, or seconds. Doesn't matter, because e to the 160 is extremely large, so it won't happen. But in the very early times, when our universe was really energetic, instead of sitting at a minima, it could actually be closer to a maximum of this potential because it has some energy. It is just like going around, and maybe it is actually closer to the top of this potential. So instead of tunneling, it can kind of roll over to a non-zero, towards a non-zero net baryon number minimum, right? So these rolling over processes called sphalerons, and they actually do happen in the early universe. So our universe was actually really changing baryon number at temperatures about 100 giga electron volts or so. And we know this rate of baryon number violation. It is actually proportional to the 5th power of the strength of weak interactions here, what is called alpha weak, times the temperature to the 4th power. So this is very good. So we actually really do believe that the standard model allowed for baryon number violation in the very early universe, even though we are not violating baryon number or matter number now. Standard model also has charge parity violation, again in weak interactions. The parity part of this, the parity violation, was actually discovered in beta decays by Chen Wu, a Chinese-American physicist. This was in beta decays of cobalt-60 specifically. When cobalt-60 decays and there's an electron produced, the electron has a preferred direction compared to the direction of the photon. That having a preferred direction means that meant that parity was violated. This is great, so because we do require, and charge is also violated in standard model, and charge parity is violated together as well. These were shown by other people. This is great because we do require charge parity violation to produce a matter-antimatter asymmetry, but for technical reasons, the CP violation in the standard model is not nearly enough to produce the observed baryon asymmetry. If you go through the calculations, you can show that the asymmetry you can produce from the standard model amount is at most 10 to the minus 20, whereas the observed amount is 10 to the minus 10. So there are 10 orders of magnitude discrepancy between what you can produce with the standard model and what is actually observed. So this is, okay, great. We have CP violation, but not nearly enough. There's also a problem with the equilibrium or the condition for non-equilibrium. For thinking about early universe cosmology, or as a cosmologist, equilibrium means just the comparing rate of reactions to the expansion rate of the universe. So you can think of this as just two particles trying to attract each other, but at the same time, in the very early universe is expanding really very fast. And so the particles are just becoming further and further away from each other, right? So there's an attraction, but then there's also the space-time is just being stretched out. So there is a competition between this attraction and the expansion rate of the universe. And which one wins depends on the rate of the attraction versus the rate of the expansion rate of the universe. This is called the Hubble rate. Hubble rate goes like temperature square over the Planck mass. And for an example interaction, the weak nuclear interactions go like temperature cube over what's called the Fermi scale square. If you compare these two scales, you see that even the weakest of standard model interactions are so fast that particles and antiparticles will always find each other and they will just annihilate. So there's no way to stop that within the standard model. It's just, everything is just too fast in the early universe. So if you had only standard model interactions, everything will just equilibrate and it will just equilibrate to zero because that's what you started with. So the standard model actually does not have any way of going out of equilibrium in the early universe. So whatever mechanism you can think of that might produce a matter-antimatter symmetry, it doesn't matter. Everything will just be in equilibrium. So whatever is producing an asymmetry will be just destroying the asymmetry at the same rate, basically. So in summary, the beautiful standard model, which explains so many things about our universe and which explains so many of our experimental observations just amazingly well, it cannot explain the matter-antimatter symmetry of the universe, because even though it has some particle number violation and CP violation, the CP violation is not enough. And then on top of that, there's no out of equilibrium process in the standard model. So this is a mystery of the overarching model that describes our universe and what actually happened in our universe. This is also a sign that we need some new physics beyond the standard model that should still satisfy the Sakura conditions, these three conditions. And of course, this new physics beyond the standard model also needs to interact with the standard model particles, because at the end, we want to produce standard model particles and antiparticles. And there are many new physics models that go by different names. For example, you can add new Higgs bosons to the standard model, which can produce this asymmetry. You can add new neutrino particles, which can explain both the matter-antimatter symmetry and also another mystery about our universe, another mystery specifically in neutrinos. You can also try to explain dark matter and this asymmetry together. And there are many new physics models that does that as well. One scheme or scenario I introduced in 2016 while visiting Oxford University, John Marsh Russell at Oxford University, was through a mechanism called particle-antiparticle oscillations to explain the matter-antimatter asymmetry of the universe. This is actually an observed phenomena within the standard model. We have these large particles called neutral mesons. These are composed of a quark and an antiquark. For example, the K meson is made up of a down quark and an anti-strange quark. And these also have antimesons made up of this. For kaon, there's an anti-kaon, which is a strange and an anti-down quark. These mesons and antimesons, there's also a B and B bar meson, there's a D and D bar meson. These can turn into each other through standard model interactions, and they show an oscillatory behavior where they just like keep turning to each other. A meson turns into an antimeson, then it turns back into a meson maybe, and vice versa. These oscillations were observed for all these mesons. You can see here the experimental data. It was also observed that there's CP violation, a large CP violation within these systems. So we wanted to look at particle-antiparticle oscillations as a special case of CP violation, because they are truly fascinating phenomena. The particle-antiparticle oscillation is just a quantum mechanical process. If you have two states, let's say two fermion states, one describes a particle and the other one describes an antiparticle, and let's also assume that they can decay into the same final state. For example, both particle and this fermion and antifermion decays into a neutron. This system can be described by a Hamiltonian written in this matrix form, m minus I over 2 gamma. Hamiltonian, for those of you who haven't taken quantum mechanics or maybe classical mechanics, is just a fancy way of writing the total energy. And I want to also mention Émile du Châtelet, who was an 18th century French mathematician, physicist, and a philosopher. And she conceptualized the conservation of total energy, which fascinates me. while translating Newton's Principia to French. So here M describes the masses of these particles. And if you remember from Einstein's famous equation, E equals mc squared, where mass is a form of energy, and gamma just explains the decays of these particles. If you find the eigenstates of this Hamiltonian, it is easy to show that the eigenstates of the Hamiltonian, which are called the heavy and light fermions, they are a superposition of particle and antiparticle states. So the particles and antiparticles, they are not an eigenstate of the Hamiltonian themselves. The eigenstates are a superposition of particle and antiparticle states. This means that in quantum mechanics, if you, for example, start with a system of 10 particles at time equals 0, and you let that system evolve, as time goes by, some of them will decay, and some of them will actually turn into antiparticles because they are just not eigenstates of the Hamiltonian. So this is a well-known process, not just for particle-antiparticle stations, but it happens with many other systems when you have a state that is not an eigenstate of your full Hamiltonian, basically. And this is what is observed with mesons in our experiments as well. The oscillations, the time evolution of the oscillations can be described by a probability. This is, you start with a system that is full of particles, and as time goes by, you will pick up some of your particles will turn into antiparticles. Let's say the blue line is for particles and the orange one is for antiparticles. And then, of course, all of your system is decaying, and you see that exponential decay envelope as well. The oscillation frequency here, so meaning that it governs the probability of turning into a particle or an antiparticle, depends on the mass difference between your heavy and light eigenstates. So delta M is mh minus ml. So the CP violation here, so this oscillation doesn't mean that CP is violated, because if this happens in both directions at same rate, then the charge and parity is still conserved. But the CP violation actually means that if you start with, say, equal amounts of particles and antiparticles, at a later time, you found unequal numbers of particles and antiparticles. That is when you know that CP was violated. This could be because maybe the decay rates of your particles and antiparticles are just a bit different, or maybe the oscillation probability for the particle to antiparticle and antiparticle to particle are just a bit different. So this needs to come from your theory, basically. And on top of all of this, the oscillations in the very early universe are actually much more complicated for the same reasons that I went through for normal interactions, because as these particles are trying to oscillate, they also interact with other stuff in the universe. It's also at the same time, the universe is expanding. So there's all these complicated phenomena that happens in the early universe, and all of that can be captured by what are called Boltzmann equations. These are set of equations that describe the number density or the time evolution of number densities of systems, basically. And I won't go into details, but this specific equation gives you 4 coupled equations that you need to solve numerically. There's a very fun effect here, which is called the quantum Zigna effect, where if your particle, while trying to oscillate into an antiparticle, if you hit it with something, you might just keep it in the particle state because interactions are observations. And if you watch a pot, the pot never boils. It's a well-known effect, basically. And this happens for quantum particles as well. It is very fun. And you can solve these equations, and they give you very interesting results where in the very early universe, particles just cannot start oscillating immediately. You actually need to wait for certain conditions. For example, oscillations are delayed due to the Hubble expansion rate. So you need to wait a certain amount you need to wait for the universe to come so large to be able to oscillate, so that your Rayleigh number is going to fit into the universe. Then if something is hitting you, like through scatterings, you need to wait until those scatterings become rare. So there's a lot of processes that hinder oscillations in the early universe, but also these processes, they also make them more interesting and more fun to study, I would say. So overall, with our in this scenario, we showed that you can actually produce a large baryon matter-antimatter symmetry. So on top of the previous Boltzmann equations I showed you, you also need to add a Boltzmann equation for the net baryon density, and you need to solve that as well. This is another differential equation. Here, this is a busy plot, but showing different abundances. So these are just number density versus the number of photons, basically, for versus time. So the x-axis is this quantity z measured in some mass units over the temperature, but for all intents and purposes, it measures time. You can see here the new particles psi and psi c. The green line is plotting their total number. The total number is going down because these particles decay, and but as they decay, they also oscillate. So even if you started with, for example, equal numbers of particles and antiparticles, so equal numbers of psi and psi c, in which case delta would have been 0. So here delta is psi minus psi c number densities. So let's say at time equals 0, you started with 0 net fermion number. But as the time goes by, there's oscillations and CPU violation, in which case, which means that you are producing an asymmetry in this orange line, and you can even see the oscillations imprinted on that asymmetry. And as these particles and antiparticles decay into neutrons and antineutrons, this also produces a baryon asymmetry, which is shown in the blue on the blue lines. So the blue lines are the produced baryon asymmetry through the oscillations and decays of these new fermions psi and psi c. The reddish pinkish horizontal line is the observed baryon asymmetry. So in this scenario, we are producing more than observed, but this is okay. This is just to make it safe, because we can tune our parameters to hit just the right spot. This is just a proof of concept that you can produce a large matter-antimatter asymmetry through oscillations and decays of these new types of fermions, basically. And these fermions are actually predicted in certain supersymmetric models, and they can even be searched for at the LHC, which we studied later in 2 different papers. So to wrap it up, our goal is to understand the universe, many mysteries of our universe. And of course, this is a hard job, and teamwork always makes science and makes everything better. And I would like to thank my team as well. You can see on the left, my students at Carleton that I work with, my PhD student, Cem Murat Ayber, and 2 undergraduate students who are doing their honors projects with me, and some previous students that I worked at in my previous jobs. And I would appreciate a lot if you wanted to come join us. Oh, also for those of you who speak Turkish, I am a co-manager of a women in science group called Bilim Kadınları. You can see our logo on the top right. So check us out as well. Thank you.
Oh, thank you very much, Dr. Ipek. Please join me in clapping or adding the clap icon to your video. Thanks very much for an interesting talk. We do have some questions that have come in through the chat, but please continue to ask questions, and our facilitators will convey those questions to me. I think the first question that I'll start with is, does baryon asymmetry happen before, during, or after the inflationary epoch of the universe's expansion?
Very good question. It definitely, well, it needs to happen afterwards. Even if some asymmetry was produced before or during inflation, the point of inflation is to erase everything, erase all prior information about our universe. That's necessary for some other property of our universe. But even if there was an asymmetry before inflation, it needs to be recreated afterwards.
Okay, and you mentioned early on about inflation. Is my understanding correct that the observations we have today are consistent with inflation, but don't yet have a smoking gun that proves inflation? Yeah.
Exactly, yep. Yes.
So students, take note. There's still plenty of work to be done.
Absolutely.
Another question: can the non-conservation of lepton number be taken as a starting point to explain the matter-antimatter asymmetry?
Yes, perfect question. Yes, this is one of the new physics models that I mentioned was called leptogenesis. And even though I exclusively talked about baryon number, at points I said matter number, and that matter number could be a lepton number as well. I myself worked on a model where none of the baryon or lepton numbers were actually violated, but there was a trick that we used where the baryon number slightly was stored in a dark sector. So there was a dark matter violation basically, and that produced a baryon asymmetry, even though there was not technically baryon or lepton number violation. But yes, you can also violate lepton number.
Excellent, thank you. And thanks for the question. Please keep them coming in. We had a question early on. How would one be able to discriminate between photons that originate from forming hydrogen versus antihydrogen during Big Bang nucleosynthesis?
So during Big Bang nucleosynthesis, actually, there's no antimatter anymore. So it's actually I should have made that more clear, that we know that at the time of BBN there was practically no antimatter. And this we know because universe was quite small actually during BBN. And if there was any antimatter, then just antihydrogen and hydrogen, or proton and antiproton, would have come together and they would have annihilated already, and they would have produced certain energetic photons, right? So and then those photons are too energetic, they would have destroyed helium, for example. So we know that during Big Bang nucleosynthesis there was practically no antimatter, and that's the 10 to the minus 10 number that we also that we can measure through CMD as well.
Okay, so the photons themselves don't differentiate, but we know for other reasons that you just explained.
Yeah.
Yes. An interesting question here. Could gravity be the source of non-equilibrium that is missing from the standard model?
Oh, very good question. So gravity, I know of a couple theories that says yes. But the thing about gravity is that we don't understand its quantum properties. So, and first approximation, I wouldn't know how to write how to write baryon number violating interactions for gravity. But I know a couple people who work on that, but I don't know where they are at right now with theorizing that.
Thank you. It's good to see all these different avenues being explored. I have one question before we have actually a question just came in, so I'll read it. Why are the dark ages called dark? The photons that escaped after atoms formation and resulted in the CMB should have illuminated the universe at that era.
Yes, good. It's because when stars first form, they temporarily the universe becomes charged again, in a way, not charged, but no, they pull some electrons and stuff, because when stars are forming, this is a very disruptive process, and that's when the universe becomes dark again for maybe a few million years.
So yeah, that's an excellent question and an excellent answer. So thank you. A very quick question. Do these beyond the standard model theories always violate baryon number systematically in the same direction? Or might they sometimes produce matter universes and sometimes antimatter universes?
Yes, technically yes. We just do, we just call whatever left the matter, because as far as we are concerned, we are the good ones, I guess. So we are the matter, and whatever is tiny is the antimatter. So we choose whatever is left to be called matter. So now you can say, oh, maybe there is a theory with multiple universes, and the same physics is just producing more antimatter on the other one. Then we need to find a way to know theirs is antimatter and ours is matter.
Excellent. Yes, and I'll just note to students, always ask your questions, because that was actually my question and it was not the answer I expected. So I learned something. Another question coming in, are virtual particles always created in matter-antimatter pairs, or will there occasionally be times when the antimatter part isn't created?
So that depends on your initial conditions, I guess. So our standard model right now is preserving matter-antimatter symmetry. So if your initial state is a net matter-antimatter zero, so if you are, for example, colliding protons and antiprotons, then whatever you produce needs to also preserve that symmetry, because we know that the standard model is not violating that symmetry. So yes, but if you start from an asymmetric initial point, then you need to then conserve that asymmetry as well. So you always need to follow the conservation laws that your physical situation tells you.
Okay, thank you very much. Our last question will sort of set the stage for our breakout room. What do you suggest for undergraduate students to improve themselves in the field of particle physics, or what kind of path should they follow in that career?
Particle physics is hard for undergraduates because so much of it involves knowing quantum field theory. But if you want as a start, I would recommend actually a cosmology class if you can take a cosmology class, or learning about elementary particles called neutrinos, which their behavior can be understood via quantum mechanics mostly. So just learning about these even the properties of elementary particles would help you a lot in if you want to go to a master's program studying particle physics, for example.
Okay, well, thank you very much, and thanks, Dr. Ipek. Thank you for the talk and answering the questions. Thank you to everyone who submitted questions, and I'll hand it over to Bill Whelan.
Okay, thank you very much, Patrick. I'm Bill Whelan. I am Vice President-elect of the Canadian Association of Physicists. At this time, I'd like to take this opportunity to thank a number of people who helped organize today's talk. Professor Dan Xiao from the University of Windsor, Francine Ford, Alicia Forgy, and Jenny Cleaver in the CAP office. The university coordinator and our host today, Professor Patrick Hall from York University. So thank you so much. And a big thank you to our speaker today, Dr. Seyda Ipek, for a wonderful, engaging, and informative presentation. So thank you. And thank you all for participating. The third talk in our lecture series will be by Kevin Hewitt from Dalhousie University and Anastasia Smolina from the University of Toronto on this Monday, February the 14th at 1:30 Eastern Time. And they will speak about the new findings from the first national equity, diversity, and inclusion survey of the Canadian physics community. So I really hope that you can attend. And now, as a reminder for all participants, that you're invited to remain in the Zoom session and to have an informal discussion with Dr. Ipek. You should see shortly an opportunity to join a Zoom breakout room, and we really hope that you participate. I'm sure Dr. Ipek would have a great opportunity to answer more of your questions, not only about her talk in this area of physics, but also career opportunities. So on behalf of the Canadian Association of Physicists and the Canadian Association of Physicists Foundation, thank you very much for participating. Have a great day. Thanks, everyone.